Hi guys, welcome back. In this video we're going to take a look at this is section 11.7 on hydrogen orbitals. And we're going to start right here with this picture. And the idea on the left side is that as the orbitals get larger and larger, they have more and more energy. To be a little more specific about that, as an electron moves to higher and higher energy levels, that electron has got more and more energy. Very much the same way that if you were climbing up a mountain, you would get more and more energy as you climbed higher and higher up the mountain. In the same way, your body does not want to be up on top of a mountain. You would, if you allowed yourself, you could fall down the mountain, but gravity's trying to pull you as close to the center of the earth as is possible. Now, you cannot get to the center of the earth, but you can get to the ground. That's where your body wants to be, so to speak. In the exact same way, electrons don't really want to be in these higher rings. Electrons do not want to be in the excited states. Electrons want to get as close to the nucleus as possible, which means that electrons really want to be in this ground state. The takeaway from this picture is that orbitals that are larger represent electrons having more energy. Here's another way to say the same thing. The ground state, and when you get to college, there are different ways to do this, but in this class, we're going to say the ground state, has zero energy in the same way that your altitude at sea level would be zero, or you'd say you don't have any energy lying on the ground. And then when you get into the first excited state, you've gotten a big bump of energy. When you go into the second excited state, you have a smaller bump of energy. The third excited state is a little more energy, and so on and so forth. Another thing to keep in mind here is that we're going to start looking at lots of pictures of orbitals, but I really want to emphasize this point. These pictures are a little bit misleading. First of all, the picture suggests that you're equally likely to find the electron anywhere in here. There's a little bit of shading, but it looks like it has a sort of constant density, so to speak. And that's really not the case. For this kind of an orbital, this picture right here masks a lot of the information that's in this picture, right? Clearly the highest probability of finding an electron is at the center, and then as you move away from the center, you become less and less likely to find an electron. The other thing that's different, or another thing that's different, is that this picture on the left has a very clearly defined edge, whereas this picture on the right is more realistic, more correct, and certainly does not have an edge. And you say, well, Cato, there kind of is an edge out there. If we made a mathematically accurate model of this, that edge would go away. But whoever made the picture had to, put an edge someplace just to make it fit. That comes up quite often in chemistry. We have pictures that are convenient, but they sometimes gloss over reality, so to speak. So this is what's real. And again, I want to emphasize this does not represent a picture of a million electrons around the nucleus. This represents a million pictures of one electron at different times around a nucleus. So without further ado, here are the s orbitals. S orbitals are spherically symmetric. They look like circles or donuts here, but in 3 dimensions they would be shells, concentric shells, with a nucleus at the center. S stands for sharp, but usually we forget about that and we just let S stand for sphere, right? So when you see these, you can think of basketballs or volleyballs or something like that. But again, the highest likelihood of finding the electron is closer to the center, and then as you move away, you become less and less likely to find an electron. We get nodes when we get to larger s orbitals. Again, these are all s. S is just telling us the shape. And then we get 2 nodes, and then we could go on to 3 nodes and 4 nodes and so on and so forth. But the s orbitals, spherically symmetric, and they nest, just like those Russian dolls. We end up with this nested set of concentric spheres. So we're going to graph these. We won't necessarily graph the other orbitals, but I do want to throw this graph at you so you can at least say that you've seen one before. The purple line represents 1s, the green line represents 2s, and the red line represents 3s. 1s has the least energy. That would be like the ground state. 2s has the ground state and one excited state. 3s has the ground state, an excited state, and a second excited state, right? The vertical axis is how likely you are to find an electron, and the x-axis is your distance from the nucleus. So in the 1s state, you're very likely to find the electron, right? There's a sharp peak right at this distance here. And then the line slowly approaches zero as you go to infinity. For all practical purposes, you're not very likely to find the electron anywhere beyond this distance right here. The 2s state has more energy. There's a small hump right in the middle where you could find the electron. Then there's a node right here. At this point, you'll never find the electron, zero probability. And then you become very likely, we get a shorter hump, but a wider hump. In other words, we're not quite as likely to find the 2s electron here, but it could range over this whole distance. That gets reflected in this picture. The center hump is narrower, right? It's narrower, not quite as tall. The next one is much wider and much taller. Significantly wider and significantly taller. You can see the density is higher right in here, right? 3s has more energy. Again, there's a small hump right in the middle and then a node, a slightly larger hump and then a node, and then this is the largest, but it's also much, much wider, right? And again, you can see that. This has the least width, this one has a little more width, and this has quite a bit more width to it. So it's several different ways of visualizing the same information. And then finally, this is how we'll usually look at these, with pretty slick pictures having hard edges. So the 1s, the 2s, and the 3s, you can compare those to these pictures that are slightly more realistic, but certainly much harder to draw. So these letters, S and P, and you can see the P's here, and later on we'll encounter D and F, are going to tell us shape. When you get into your college chemistry, they'll probably talk about quantum numbers, and we're not going to do that in this class, but they'll talk about how the letter indicates the shape of the orbital. So P now has a node in it, right? There's two lobes with a node separating them. That's not the case with the s orbital. The s orbital is spherically symmetric. And you say, well, there's a node right there. True enough, but that node isn't separating two lobes, right? Whereas in this p orbital, the electron can be in the orange area or the blue or green area, but never in between. The other thing that's different is that there's only one 1s orbital. There's a single 2s orbital. There's a single 3s orbital. In the language of chemistry, we'd say that the s orbitals do not have sublevels. What that means is that because these s orbitals are spherically symmetric, it doesn't matter how you rotate them in space, they always look the same. Right? When you take something that's a sphere like a pool ball and rotate it, unless it has some markings on it, you can't tell which way it's rotated. That's not the case anymore. Now we can orient the p orbitals that have these two lobes in the x direction, in the y direction, or in the z direction. The result of that is, since we live in a universe with three spatial dimensions, there are 1, 2, 3 p orbitals, right? To be slightly more correct, we would say there is a single p orbital with 3 sublevels. So now orientation in space matters. The other thing you'll notice is that this is 2p and 2p and 2p. There's a 1s. Why is there no 1p? Well, we'll get to that later, right? But it turns out the p orbitals do start with the number 2. This video will be continued where we'll look at d orbitals and f orbitals. So this is just part 1.